Hello and welcome back, IB Math AI students. Today we are finishing up Module 3 with Lesson 10, Volumes of Solids. The EQ is really a task. I want you to be able to describe a general process to find the volume of a prism. My goal eventually is to not necessarily rely on a formula booklet, but for you to be able to build these formulas so you can do these things intuitively. Before we get there, let's take a look. Now, the volume of a solid is the amount of space it occupies. Finding the volume of uniform figures really isn't just too bad. You do need to know those formulas. I'm sure many of you have learned these throughout your days as being geometry students, but we are going to change them just slightly. Now, for solids of uniform cross-section, we say that the volume is the area of a cross-section times some kind of distance or some kind of length. This is probably very similar to what you have learned before, which is area of your base times its height, or area of a base times a distance like the length. So that's what you used to do. But we want to focus on the idea of a cross-section. So the cross-section can take many different shapes, right? The examples that we see below, this is going to be a cross-section. It's something that you can draw inside at any point in that solid, and it's going to be the same at multiple points. So there we can see that triangle can be extended throughout its length. This circle can be extended throughout the length of the cylinder, and we get a bunch of different congruent circles. Uniform here is what we are focusing on. Uniform cross-section means that no matter where you perform that vertical slice, the cross-section will be the same. This is why we call these solids of a uniform cross-section. The cross-section should be congruent to the base or face, which is why these two volume formulas are technically the same. So let's go ahead and go through a couple of examples here where we are going to calculate volumes of these different prisms. Okay. First one, we've got a nice rectangular box. Now, again, depending on the way you want to look at this, it doesn't matter what you choose really as your cross-section for a rectangular prism, but I'm going to choose this as my face that's going to be my cross-section, okay? And that has a dimension set of 4 by 1. So there's the area of my cross-section, 4 by 1, and then I'm going to multiply it by the length here, 6. That's easy enough to say that's going to be 24. These are all in meters, and remember the volume is going to be in cubic units. So 24 meters cubed for that box. Now, the next one is a triangular prism. It gives us the area of ABC. Well, that's perfect. That's a triangular base. So that's going to be like our cross section. It's applied across a height of 7.5 centimeters. Well, the area of that cross section is told to us here. Perfect, 12 centimeters squared. So we say that's going to be our area, and we are going to multiply it across its length, which in this case is going up vertically. It's a height of 7.5. Multiplying those two together, and we are going to see an area of 90 centimeters cubed. I'd like for you guys to go ahead and do example C on your own, and we'll go over it, make sure you got it correct in class next time I see you. All right, so that does it for our basic solids, which we call prisms. Now we move on to something a little more complex, tapered solids. These are your pyramids and cones. Now these solids do not have uniform cross sections, so those previous formulas don't work. These cross sections are going to be a set of similar shapes, and that similarity is really important. They get smaller and smaller as you approach the apex, but they are similar shapes. We don't have time to derive these formulas below, but trust me, they are a fact. So for any tapered solid, like a pyramid or a cone, you can find it as 1/3 of the area of the base times its height. So now we don't think about it as cross-section because we need the biggest possible cross-section, and the biggest possible cross-section is going to be at its base. Now, very similar to these tapered solids is a special case one, and that's the sphere. So the sphere is going to have this formula 4/3 times pi r cubed. I'll do an example of a pyramid. You go ahead and find the volume of the corresponding sphere. So here we can see the dimensions of our base are going to be 5.1 by 2.3, and we have a height of 6.8. So I'm going to mark a couple of things here, and then I'm just going to apply that 1/3 area of the base, which is a rectangle, 5.1 by 2.3. And then we are going to find the height, plug that into our formula as well. And when we multiply all of that together, we get 79.764. This is an exact value, centimeters cubed. If you wanted to round it to 3 sig figs, you certainly could. and that's going to be 78.0. Oh, excuse me, that's going to be 79.8 centimeters cubed. Either way, we've got a volume there. Next, I want you guys to try and tackle this sphere problem. Lastly, we want to put everything together, and this is what we call composite solids. Many real-life objects are made up of these basic solids, these spheres, cones, pyramids, and prisms, but you can find a rough estimate for the volume of pretty much any object that you see in the world by breaking them down into separate parts of those basic solids and putting them together. So, let's go ahead and take a look at an example. In example number 5, we have a small warehouse that has the following shape and needs to be air-conditioned. Air conditioning, or AC units, are measured by the ton and sold in increments of half tons. For one particular brand, a 1-ton AC unit will cool a volume of about 300 meters cubed. We want to know what size in tons will this AC unit need. Round your answer up to the nearest half ton. Well, since we're talking volume here, we need to find the volume of this shape. Let's go ahead and start by looking at the rectangle prism part here. So we've got a rectangular prism. Here's my cross section, which features that 6 by 11 face. So the rectangular part is going to be 6 times 11. And then it is being extended across this entire length here of 15 meters. So we multiply that together, and that's going to give us 990 meters cubed. Now, the triangular part is going to be a little bit different, but it's still one we've already worked with. Finding that triangular part, it has the 1/2 base times height. That's the area of the cross section. So we have 1/2. Our base is going to be that 11. The height is going to be 5 that stretches up vertically. And then it does extend across that entire length of the warehouse as well by 15. Multiplying all of that together, and we should get 412.5 meters cubed. Thus, we can see that our total volume is going to be the sum of these two, 990 plus 412.5, which is going to give us 1,402.5 cubic meters. Okay, so there's our total volume, but that's not what the question is really asking. The question is saying, well, how much air conditioning do we need here? Well, it says that a 1 ton is going to handle 300 cubic meters. Well, we've got 1,402 cubic meters. So how many tons is that going to be? So the total number of tons will be 1,402.5, and then we're going to divide that by 300. When we divide that by 300, we get 4.675 tons of basically air conditioning power that are needed. So is there going to be a company that's going to sell a 4.675 ton machine? Probably not. So look at what we're supposed to do here. We are supposed to round our answer up to the nearest half ton, okay? Because that's how it sells it. Now, you might look at this and say, oh, well, 4.5 tons, that's going to be how much I need. That's the nearest half ton. But remember, we want to round up because 4.5 tons is not going to be enough. The air conditioning unit is going to be overworked. So we need to round up. And the nearest half ton would be at the 5th ton. So that's the air conditioning unit that we need. Okay? Your task next is to work with the volume of an ice cream cone and scoop on top, break down the shapes. Do this you do, we'll check it in class. Thanks for watching. I'll see you next time.